Okay, welcome to Bio 101. Who knows that biology is the study of life? Who knows that already? Who did not know that? If nobody raises their hand, I'm going to assume that the people who didn't raise their hand meant to raise their hand. 3, 2, 1. So you all know that biology is the study of life. Perfect. You know what that means?
That we are biology?
It means we get to skip chapter 1 and go right to chapter 2. Is what it is. I don't have to say, so class, what's biology? And somebody's going to say, ooh, it's a study of life. You know, like they learned it because they were a bio major in high school or something.
Wow.
You know. Like, yes, we all know biology is the study of life. Did folks take bio in high school? Anyone else? Anyone? It's pretty. Did anybody take something other than biology in high school? You didn't. So you didn't take bio in high school, or you took?
Yeah. I did a scientific high school in Italy.
Okay.
So took biology, chemistry, physics, math, 2 foreign languages.
Let's switch places. You should be up here,
Latin.
and I should be over there in that seat, learning bio from you. Very cool. What part of bio did you like the most?
I don't like science that much, to be honest.
Overexposure. You took so much of it, you hate it now, right? It's like if you eat nothing but cake, you don't like cake.
Yeah.
It's kind of like that. I hear that. I was thinking.
Anatomy.
Oh, anatomy's awesome.
Yeah.
Yeah, anatomy is a lot of fun. There's actually, you think of anatomy sometimes as you just memorizing a bunch of sort of stuff, you know, like names of things. Anatomy is actually quite exciting. I guess you have to be a little bit into it before you can get to the level of exciting with it. But it's pretty neat. It's pretty neat.
And lab.
Yo, lab is where it's at. Lab is where it's at, for sure. A lot of drawing. Yeah, a lot of drawing in it, and that's fun as well. Who else took bio in high school and actually remembers it? Anyone? What do you remember from high school bio?
Mitosis, meiosis.
What's the difference between the two? Do you know?
That's why I went wrong.
So
Those
yeah.
are the ones that.
Yeah. You don't remember the things you remember, but you remember the things you were traumatized by.
Yes.
Right?
Yes.
They're burned in. What do you like about your bio?
Me?
Yeah, you.
Mitochondria and like the cycle of Krebs and also DNA, RNA.
Krebs cycle, cool.
Study of population.
I was just listening to a podcast yesterday on the Krebs cycle.
Really?
Yeah. I'm sure you would all find that very interesting. I mean, how many podcasts where the episode is like literally the Krebs cycle, though? It's pretty interesting. It was a whole episode on the origins of life and how complex biochemical pathways come to exist. And it was like focused centered on the Krebs cycle, which is the coin of the biological realm in terms of energy production and how you do stuff in here. You know, without the Krebs cycle, you've lost it all. I mean, it's how do you make ATP? Anybody heard of ATP before? Yeah, it's how to make ATP. It's how a lot of amino acids are synthesized. All kinds of stuff uses the Krebs cycle. We'll get to that in 5 or 6 weeks. I think we'll get to the cycle of Krebs. The cycle of Krebs. What else do you remember from high school bio? Who remembers going to high school biology? It's been a while for me, but I remember going a couple of times, but I don't remember much of it from there. What did you do in your high school biology class?
There was like one time students had to like dissect animals.
Animals, which ones? Giraffes, hippos?
I think it was pigs that they did.
Pigs?
Yeah.
Cool.
The baby pigs.
The baby ones. Oh. What else?
We learned a lot from Amoeba Sisters.
From what?
Amoeba Sisters. We kind of just like watch those all the time.
So you went to bio class and watched YouTube? Okay, cool. I'm streaming to YouTube now.
One thing I'm traumatized of is the counting and the study population.
Oh, cool. We'll get to that in Bio 102.
Again?
You haven't done it like we're going to do it. It's great. It's going to blow your mind. What else did you do in bio? Nobody looked at a cross-section of an onion under a microscope and looked at cellular divisions. That's a common thing. So people are like, why is it always an onion? Like, why is it always a cross-section of an onion? It turns out onion nuclei look like the ones that the textbooks like to show. If you look at the nuclei of like animals as they go through meiosis or mitosis, they're a lot messier. Like onion, allium nuclei, allium root tip nuclei are these perfect little mitotic things where the chromosomes separate perfect, almost every time and they line up right down the middle. So the sort of the textbook example that nothing actually looks like when you look at it in nature. Like the diagrams of the fetal pigs in the lab manuals. There's not a single fetal pig I've ever seen that actually looks like the one in the manual. Because I used like the hyper idealized thing. It's like Instagram. No one on Instagram actually looks like they do on Instagram. They're sort of the idealized versions of themselves that doesn't bear any resemblance to reality at all. So this is bio. How's it going so far?
Great.
Perfect. What do you want to learn? Like, what do you want to know? I mean, again, your 2 bits, I already spent it. What do you want to know? Any question you want for the next 5 minutes. Ask me anything. Anything at all.
What's your favorite color?
It goes back and forth between like a forest green and purple. Purple?
Yeah. My dad.
Nice. It depends on how I'm feeling on that day. If I'm feeling calm, it's kind of greenish. If I'm feeling regal, it's purple. Hell yeah. Hell yeah.
My least favorite color is green.
Your least favorite color is green.
I know. That's the only green thing.
She loves her shirt too. It's like the color green. She would prefer not to wear it. Other questions? Green or purple?
What's your personal background in studying biology?
I have a bachelor's degree in biology from Southeast Missouri State University. We called it Harvard on the Mississippi. It was not a little state school in southeastern Missouri. I stayed there and got a master's degree in vertebrate ecology with a background in GIS, Geographic Information Systems. From there, took a couple of years and I worked as a statistician in the St. Louis Public School District and in the St. Louis County Health Department, capturing mosquitoes for their encephalitis survey. So there's a strain of encephalitis called St. Louis encephalitis, and it's carried by mosquitoes in St. Louis. It's not like some big outbreak or anything like that, but it shows up every once in a while, and you don't want to get encephalitis. And so they paid me to drive around St. Louis County in a truck and capture mosquitoes and send them off to, interestingly, the person who diagnosed the mosquitoes for the encephalitis virus was at Southeast Missouri State University. And it was fun. And I had a couple of hits. I actually captured a couple of mosquitoes that was carrying St. Louis encephalitis. After that, I went back to graduate school because I figured, why not? Why not? I got a doctorate from the University of California at Davis in paleobiology, study of life on Earth as evidenced by the fossil record. That was in 2006. Go Aggies, West Side. So, yeah, California is a weird place, but I loved it. So, yeah, it was good. It was good, And then from there, came out here and bounced straight into Nova, teaching bio. I used to occasionally, I would teach physical and historical geology every once in a while. Every once in a while I teach zoology, study of the animal kingdom. And every once in a while I would teach a natural history class, but I mostly do the bio 101 and 102. Mostly. So what I'm saying is, like before, we'll get along fine. My actual, if you look at my doctorate, it says Doctor of Philosophy in Geology because the paleobiology program at Davis is in the geology department. So it's like master's in bio, PhD in geology, but technically I took two geology classes in my entire life. My doctorate's in geology. So that's my deep dark secret. Yeah, you can take more geology classes at Nova than I have with my doctorate. So it's fun. I think I took a stratigraphy and a physical geology course, which was fun. Go ahead.
What's your favorite class you've ever taken?
Taken?
Yeah.
My favorite class I've taken. Not that one. When I was an undergraduate, when I was an undergraduate, I think favorite.
You can name a top three.
Yeah, because what do you mean by favorite? Because the most transformative class I took was one It was just like intro to philosophy 101. And what it rearranged a couple of things in my brain. And I think it was just a right time, right place, right content kind of thing, where I went from being really, really bad at mathematics to being really, really good at mathematics and actually getting a math minor because of something weird that happened in my brain in that philosophy class, which was weird.
Yeah, right. I took it for 3 years. Philosophy for 3 years.
Philosophy?
Yeah.
Yeah.
Nothing changed. It's the same.
Well, the diagnostic is not the philosophy class. It's math, right? It's math, right? So your math has not. Since you took it.
It was bad for 7 years until I came here.
So you're actually getting worse at math.
No, I'm worse there. I'm good here.
Okay, perfect. I also liked a research experimental design course that I took, where it's like how do you actually design experiments. I just had a really good professor for that, as well. And we did a lot of. It was like how do you choose the question? How do you come up with the design? How do you choose the stats to use? And then like do it. And it was a good class. That was a really good class. It set me up pretty well for graduate degrees and things like that. Anything else?
What's your favorite sport?
My favorite sport, hockey. To play or to
To watch.
watch? Probably hockey. Yeah, probably hockey. Yeah. Yours?
Badminton, soccer.
Oh, fun. Very cool. Questions?
Can I know your email address?
Sure. P. Fitzgerald. I'm going to write it on the board.
Okay, thanks.
That's a period, right?
I think it's an ad. I think it follows the traditional email formatting customs. Period, yeah. I do it sort of a dash. I get it. One more. Anything else?
What's one thing in biology that you like to teach that you're really passionate about?
One thing
That you like to teach in bio?
that I like to teach. Oh, my favorite bio topic,
Yeah.
kind of. $101 or $102?
Your choice.
I like that. In bio I'll do one of each. In bio 102, I really like circulatory system. It's a lot of fun because it's a lot of physics. It's fun because it's a lot of physics, right? And that's what you're in for this semester. Bio 101, probably respiration, I think. Respiration. And that did not used to be the case, but it seems to be. People, genetics is so fun. Gregor Mendel is not interesting. Okay, a lot of people like when we get to the heredity stuff, which is kind of towards the end. It's like you learn about Gregor Mendel and P's and dominant and recessive and traits going through time and traits expressing in the body and things like that. Mendelian genetics applies to maybe 7 characteristics on your entire body. Everything else genetically is really, really complicated. It's like you have 11 genes just for eye color alone, and they're all interacting with each other with other weird stuff. So it's like, let's learn Mendelian genetics that will not apply to you, except for like whether you have a widow's peak, what thumb is on top when you cross your hands, and your blood type. It's like there's not a lot of pure Mendelian one gene dominant expression kind of stuff you have. A couple of disorders, cystic fibrosis, right, is the big one. I think that is a pure Mendelian dominant recessive kind of thing, but not much else. You know about the thumb thing, right? So if you fold your hands like this, right, which thumb is on top?
Right.
Raise your hand if it is your right thumb. Weird. Left? Okay, now, indifferent.
It just depends on how I feel.
Oh, interesting. Okay, so fold your hands the way that you prefer. Okay, now we're gonna hear the sound. Now flip it to the other way. How's it feel?
Weird.
Weird, some people say gross. Occasionally you get a, huh. Can you write equally well with both?
I'm getting better at it.
Mildly
I used to be
ambidextrous, yeah, mildly
ambidextrous.
ambidextrous, very cool. Neat. Yeah, for some weird reason, that seems to be a Mendelian hereditary stupidest trait you'll ever think, right? Because it's like, why would Darwin care about what thumb? Why is that why is that genetic, you know? Why do hands fold so comfortably and easily anyway? It's like they were weird, you know? So there's a lot of stuff in bio that we don't know that is interesting. And there's a lot of stuff in bio that we don't know that is either just not interesting or just a dumb question or just try to get funding to study why your thumb is on. I mean, it's not going to get funded by the NIH. You know, it's like, I want to answer the question about what determines which thumb you put on top when you cross your. There's a pandemic going on, for Christ's sakes. We can't waste our money and time on that. So if you come up with any other questions that you would like to ask throughout the semester, feel free to ask them. Yesterday in my Bio 102 class, I got, do you believe in heaven? What happens when we die? And what did your parents want you to be? Right, so that's a pretty interesting one there. Then as well. It was all good fun. All good. And if you to whom, you can probably make some inferences on what's going to happen here. So if I gave you a big stack, just take it and make it rain. Distribute it amongst. I'm going to do something I've never done before, and I was not kidding when I said this. I'm going to skip chapter 1, right? Because I don't want to talk about it. Because we have actual things that we want to get to. Chapter 1, read it if you'd like. It's all philosophy, deductive and inductive reasoning, hierarchy, going from big things to small things. We'll get into all that as we go through. We don't need to spend the whole time in chapter talking about it. What I do want to get started with, though, is like actual things that you could turn in for homework.
Sorry, I have no idea what it is about. So it's on chapter 2?
This is stuff that is content from chapter 2.
Okay.
Right? And I'm just giving this to you so you can turn it in. When does class go to? 10:50?
I think like
10:55? We might be able to get this done by the end of the day. Might be able to get this done by the end of the day. So the trick is to not pay attention to the thing I handed out to you. Thank you. All right? It's gonna be great. We'll get to this sort of as we go. What I really want to get to today is, let's just dive right in. Who loves atoms? Some of your best friends are made of atoms. You should appreciate them. I am made of atoms. You are made of atoms. If it wasn't important, that wouldn't be the only poster we have in the room twice. Do you need one? Do we have any extras out there floating around? 30, there should be. Okay, perfect. Got it. I like to get, I was thinking about this when I was planning my lecture on the way to class today, when I was walking down the hallway thinking about what I was going to do. I thought, you know what, let's get right to it. Why do we need to screw around with the intro stuff in chapter 1? So we have one poster in this room twice, and we'll be referencing it quite often throughout the semester. It turns out and I also want to impress upon you the realization and just kind of reinforce this. This is a biology class, it's not a chemistry class. So if you hate chemistry, don't freak out. Yes. Okay? So it's like, there's gonna be some chemistry, but we're not gonna get bogged down in it. We're gonna keep our eyes on the prize of biological systems. So for some folks who took a bit of chemistry before, today might be a little bit of a review. If you have never taken chemistry before, or this would be a delightful refresher for you, this will be a delightful refresher for you, and it'll be fine. Good. Always remember, if things start getting a little bit, if you want me to slow down a little bit, because I'm sort of a fast talker, if you want to hit the pause button and tell me to slow down, if you want to go through something again, we can absolutely do that. Raise your hand if you are brave. Raise your hand if you're brave. right? So actually saying, hey, can we slow down a second? Can you go over that again? Sometimes it requires a bit of bravery. You with me on that? Because it's like, what do you feel when you're thinking that? You feel like everybody else is fine, but I don't understand this, and it's only me, and everybody else has a doctorate in this already, and I'm the only one who don't. You know, like the brain says things that are not true. Typically, when somebody has a question, you've heard this before, when somebody has a question about something, usually young people have the same question. It serves us all by going through topics multiple times if somebody has a question about it. And when you're wondering whether or not you're going to get left behind, when you're wondering, if you're ever wondering if you should raise your hand, and if you have the courage to raise your hand and ask to go over it again, I love you and everything is going to be okay. You probably read my Rate My Professor, you know what you're in for. Somebody said it's a cross between a long time ago, Gordon Ramsay and RuPaul. Okay, let's get right into it. You are made of atoms, okay? And darn it, I'm regretting skipping chapter 1, right? Because like atoms are made of smaller things and they combine together to make larger things. But when we talk about biology, most of the time, we don't need to spend a lot of time going to the things, like the origins of things below the level of the atom, all right? I mean, sure, we'll talk about protons and neutrons and electrons and all that other kind of stuff, but we don't need to go all the way back to like string theory and mathematics and all of that. It's not sort of a thing. So our biological life sort of starts where the periodic table sort of is and what those things are. So carbon? What do you say?
Isn't it like almost everything?
Seems appropriate for a biology class, doesn't it? You know, so it's like, let's start there. So when you're looking at the periodic table, so far so good, right? This is the atomic symbol. It tells you what the element is. Some of the periodic tables will actually say in the bottom, carbon or something like that on the bottom. There's a couple of things up here. For carbon, there's a number 6. Who knows what that is?
You know his number?
Correct. Which equals what? Correct. It is the number of protons. So all atoms are made of protons, neutrons, I'm going to put an asterisk next to that in a second, and electrons. Protons and neutrons together form the nucleus. The electrons zip around the outside of the nucleus. Is this review for anyone? Perfect, perfect, perfect. There's an asterisk here because there are some cases where there will be no neutrons present in the nucleus. So it's like, usually there's neutrons, almost ubiquitously there are, but there are a couple of cases where there's not. So I'll just put an asterisk there, but the right answer on any exam you have from henceforth is protons and neutrons are in the nucleus, right? So it's like, don't make it too complicated. Perfect. So far, so good. So how many protons does carbon have?
6.
6. Class?
6.
1, 2, 3.
6.
Do protons have a charge?
Yes.
Yeah.
What is a charge?
Positive.
What is conceptually a charge?
The I was about to say like
It's a quantum interaction between oppositional states of being, right? So it's like people, like when people think of charge, they think, yeah, positive, negative, obviously, but it's like, what is a charge? It's like conceptually, what is charge? And it's like, it doesn't exist without its opposite, right? It's sort of this dualistic state of oppositional force, which is part of essentially universal field theory. It exists because of electromagnetism, sort of demands it, right? Electromagnetic fields sort of demand it. Do protons have a charge?
Yes.
Yes, what is it?
Positive.
Says who? This is trivia. Do neutrons have a charge?
No.
No, so they're like a television set. I just kind of put a little zero there. They take up space and they add mass, but they don't have any actual value whatsoever in field of electromagnetism. So they are about the same mass as a proton, right? So neutrons and protons, same mass. One has a positive charge, one is neutral. Electrons have a charge?
Yes.
Yes. Negative. Awesome. So you know who came up with this positive negative notation concept for this? Benjamin Franklin. Benjamin Franklin. Remember the flying this kite with a key on it situation? If you have taken American history or older than 250 years old, you remember this. So I remember it, but I've read about it. Yeah, trivia. Ben Franklin. Who knew it's like positive and negative? Cool. Awesome. Very neat. Very neat. So if these have, I'm going to go like this. These two things have measurable mass. If we want to know how much something sort of weighs, right, what its mass is, right, we can say, well, pretty much, okay, so what is the total mass of the protons and the neutrons together? And we call that the atomic mass. For carbon, it is,
6.
12 point something.
yeah, it's up there, right? For those of you who are not nearsighted, help me out. What do we got?
12.01.
0.78.
0.01.
078.
Cool. Cool. So this is atomic
Mass.
mass. What is mass?
Like the volume something trace up.
I just call it like the amount of stuff. Like actual tangible, takes up space. Currently, we would say interacts with the Higgs field, right? Mass. Okay. The mass of a proton is
The atomic weight.
1. 1 Dalton. It's the unit called the Dalton. The neutron has the same mass, 1 Dalton, which is neat. Anybody take chemistry in high school? Perfect. You ready for this one? Here's the magical stuff that people didn't tell you before. That's good. You're going to see this and you're going to go, oh. Do you remember Avogadro's number?
Oh,
It is a really big number.
an A.
6.02 times 10 to the 23rd power. It's called Avogadro's number, the mole. The
Oh.
mole, right? This is if you have 6.02 times 10 to the 23rd of something, you have a mole of it, right? 6.02, yeah, the guy who developed that was Avogadro. 6.02 times 10 to the if you have 6.02 times 10 to the 23rd, so it's like extend this decimal 23 places out this way. Daltons equals 1 gram. .02 times 10 to the 23rd atoms of carbon is 12.01078 grams. Good?
Yes.
Perfect. So if a proton has a mass, atomic mass of 1, and neutrons have an atomic mass of 1, what is the question that you would like to ask me about this atomic number? Why is it a decimal? Wouldn't it just be 12? What's with all the decimals? What the hell? Correct? Can you see if I write here? Things called isotopes. Isotopes. For carbon, there are 3. It's carbon 12, 13, 14. Carbon 12 has an atomic mass of 12. Carbon 13 has an atomic mass of 13. Carbon 14 has an atomic mass of 14. Class?
14.
1, 2, 3.
14.
Yes. If nothing else, your caregivers are going to talk to you about how your day of class went, and you're going to say, carbon 14 has an atomic mass of 14. Cool. If you look at all the carbon that we can find in the known universe and see, 97% of it is carbon 12. Carbon 12, 6 protons, 6 neutrons. Carbon 13 is about 2%. And it has 6 protons and how many neutrons does it need to get to 13? So that number would be 7. And carbon 14, how many protons does it have? Because it all has 6,
Yeah.
right? Cool. So, running out of board space. 12 times 0.97, 13 times 0.02, 14 times 0.01. Average them out, you get 12.0106, whatever, ish. So it's the weighted average of the 3 isotopes of carbon. Overwhelmingly, I mean, just from looking at the atomic mass, 12.010, blah, 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 right? You can just see, just from that, it's like most of the carbon in the universe is carbon 12, right? I mean, the number's close to that, right? And there's a little bit of carbon 13, and there's even little bit of carbon 14. But overwhelmingly, it's carbon 12. Cool. So that represents like the weighted average of the isotopes of carbon. Good? Perfect. Any questions so far?
The words after electrons.
Zip around outside. The summer is a wonderful time to learn about chemistry. So if you go outside on a lovely Virginia afternoon in August, around 2, maybe 3, it's hot, it's humid, it's gross, you're turning into a liquid, right? Your cell membranes start to lose their stability and you feel all gross. Yes? Yes?
Yes.
So your head represents the nucleus. The gnats that are zipping around your head are the electrons. That's sort of how it works, right? So you have this large mass-filled stable thing, this core in the middle, and the electrons just sort of buzz around like gnats around your head in a Virginia summer sort of day. Good? Good. We don't draw them that way, though. We draw them in different ways. Not to represent reality. We draw them in ways to give us structural models about how things work. All right? I'm going to do some erasing. Is that okay? Ooh. I'll take pictures first. Good idea, right? For some reason, my camera's always insulting. I will post these on the canvas. I'll leave that, I think. I'm gonna teach for a living, I should improve my handwriting. 6 protons, 6 neutrons, good? So it's like, I didn't draw every proton here, I didn't draw every neutron. For a nucleus, I'm just gonna draw a circle, and just write 6p, 6n in the middle of it. Convention, good?
Okay.
With it? You with it? With it? Perfect. I like to draw electrons as x's, and what that means is that so do you.
Okay.
I've answered a question for you, right? I've made it easy. If we want to draw this in a way that is chemically, electrostatically neutral, we have 6 protons, we'll need 6 electrons to go around it, right? Yes, I know there are things out there that exist in the ionic state, +1, -1, we'll get to that later. For today, we'll draw things electrically neutral, and we'll get to ions probably on Thursday. Good? Perfect. Cool. So if I want to draw some electrons around this, I want to do it in a way where it's not just 6 electrons, woo. I want to do it in a way that provides predictive power, that I can actually work with it for molecule building, molecule building, okay? And the periodic table is set up in a way that helps us out with this. Because if you really understand how the periodic table is set up, all of these questions about how to draw elements, atoms, molecules are answered for you in the structure of the periodic table. Okay? So I will demonstrate this. Now, 6 electrons, I'm going to put 2 next to each other, just like that. And I'm going to call that shell 1. How many do I still have left to do?
2.
2 what?
2 cells.
How many electrons do I have left? 6 minus 2.
4.
4, yes. Took this great philosophy class, really helped me with my math, right? Expressions. 1, 2, 3, 4. Carbon. Carbon. Woohoo. Questions, there are about 9 questions you can ask about this if you haven't seen this model before. What are these things? We call them shells. Why are there 2? Well, in this case, there are 2 because you can only fit 2 electrons in the innermost shell. Okay? So this is like a 2 max situation. The next shell out, larger, that's an 8 max situation. If I ever get to element number 11, what's element 11?
Sodium.
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 I'm going to need
3.
a 3rd shell. Okay? So just so you know, for these shells, shell 1, 2 electrons, shell 2, 8 electrons, shell 3, 8 electrons. We can go to shell 4. We're into the metals at that point. We've sort of left biology and we've entered transition chemistry. Okay, so it's like for bio, we don't get into the 4th row that often, right? I mean, once you get to chlorine, you're pretty much there. I mean, yeah, you do some cool stuff with the elements below that. I mean, what's some of the cool biological stuff you use that's lower than argon up here? Iron at 26. What do you use iron for?
Blood.
Blood. Right? Right? Blood, yeah, so you're chock full of iron. Iodine in your thyroid, right? For like it's an intermediary and some hormone production. What else do you use? Calcium, potassium, like tiny bits of copper. I mean, if you ever take a multivitamin and you read the back of it, like you get all these like micro doses of some of these exotic kind of things up there. You don't use any plutonium or anything like that, I'm happy to say. A little bit of bromine, right? But most of practical biology is element 17 and up, right? I mean, you don't get too much into the weirdo stuff in a bio class. So this will do it for us. This will do it for us here if we go up to these three. You can now answer, I think, 4 of these questions on this piece of paper just from this. Let's practice some. Well, you can definitely do the first one, right? The first square. Yay. You want to take a minute and do that and have it done? Class, 1, 2, 3.
Yes.
So in that square, you're pretty much drawing like that. We don't learn as much with our brains as we do with our hands. We don't have any covalent bonds in this one, so we don't need to do that one yet. Got it? We there? Who's brave? Perfect.
I have 2
Do
questions.
oxygen.
Oh. Okay.
Oxygen. You have 27 friends that are happy to help you.
Okay, because I'm blind. Okay.
So far, so good. Atomic number of oxygen.
Oh, you want me to do the square? Oh.
No, just, yeah, do the actual thing. Yeah, you're good. Keep going, keep doing what you're doing.
Okay. What's the proton number? Like the 8. 8? Okay.
It's the mass. Close, probably, how many neutrons should we put?
8.
Probably 8, yeah, it's like 15.9, so 16-ish, so yeah, 8 neutrons. So how many electrons do we need?
8.
2.
Does it matter the placement? No, right?
Not yet,
Oh.
not yet. It might on Thursday.
Okay. That's good, right? Just 8.
Is it good?
No.
Doubt creeps in so quickly.
Yeah.
We have a lot of holes in our heads. 1, 2, 3, it's like so many places for doubt to creep in.
It's the same amount as the neutrons, right? Electrons.
The neutron, say again?
Isn't like.
We want the electrons to be the same number as the protons.
Okay, so same.
You're good, yeah, so in this case, it's the same.
So I got like,
How'd we do? She there?
yes.
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 Class, 1, 2, 3.
Yes.
Yes.
Good job. Who's brave? How many people raise their hand now, right? You want to knock out sodium? Sure.
Are there no covalent bonds in
Yeah, so sodium 11. So yeah, right. Sodium is 11. And look, we're looking at a
Na.
22, so 23 atomic mass, give or take. I got that chalk imported from Japan over the summer.
All that for chalk.
Horigomo chalk, yeah.
Is it?
It is
better
nice
than
chalk.
yours?
Yes, it is nice chalk. I'm really happy about it. It's like it is. Because like I run a minimalist classroom, so it's like I'm gonna splurge on anything. I have like one option, chalk. Well, I guess two, good erasers.
If you want us to round up to 23, would there be 12 neutrons instead of 11?
Yes.
Huh.
Yes. So they're not always the same, right? They're not always the same, right? Round up. Well, yeah, we'll adjust in a second.
What is the mass finish?
Mass is 20, we're rounding up to 23 on mass.
Okay, so it's about the, okay.
There we are. No, that's it. You're there. 11. And give yourself another neutron in the nucleus there. We'll go up to 12 since it's close to 23. Is he there?
Yay.
Class, 1, 2, 3.
Yes.
Good job. Who's like wildly lost? Anyone?
So I have a question.
Really?
Okay. Chemistry was never.
I should have said, really? Really? Questions?
How come, okay, so
Yeah, so let's pause here. It's like, let's all get caught up to where we are, right?
how come, so I'm just not getting why there's only one electron on the top.
You can only put 8 electrons in the second shell and we have 1 left over, right? So it's like, it's 2, 8, 8. So once you hit 10, you're full. When you go to when you add that 11th electron, you need to put it in another shell
That's what I was.
farther out. So, I mean, it's essentially no different than this classroom. So how many students can you put in the first row? 1, 2, 3, 4, 5, 7. So it's like, if we have this rule where as students enter this room, they're going to fill seats from this direction outward. So the first 7 students are going to be in this row. If an 8th student comes in, where are they going to sit? They got to be over here. So that holds 1, 2, 3, 4, 5, 6, 7. This holds 7 as well. So the 15th student is going to be in this row. So it's like, you can picture this atom in these shells exactly like this classroom. This row holds 2, this one holds 8, this one holds 8, this one holds 18, this one holds 18. These people are in the metals at this point here. This one holds 30 something, whatever, far and farther out. So, and that rule holds, right? When electrons are added to a nucleus, to an atom, they will always occupy the shell that's closest in to the nucleus. Right, and they'll go outward from there. So this third so it's like, here's our 2 in our innermost shell. This is not a big shell, it's really, really small, right? It can hold 2 things. Remember that these electrons have the same electrical charge. So these electrons are they're repellent to each other. You cannot squeeze 3 things of the same charge into a shell that small without one of them just getting, it's like, you know what? it's too negative in here, I'm going to leave. Now pop out to a new spot in the next one farther out. You can fit 8 before the electrostatic repulsion kicks the next one out to the next level. So there's like actual like tangible electromechanical physics answers, just like 2, 8, 8, that's dumb. It's like, yeah, kind of, but it also makes sense in some weird ways because it just comes down to the geometry and physics of electrostatic. It just comes down to the geometry and physics of electrostatic repulsion as electrons occupy nuclei. Right? I make it sound douchey when I say it like that. Go ahead.
So, on the outer shells, like, it's always gonna be how many protons there is, because it's electrons, it's not gonna match the neutrons, right?
It's not gonna, it might match the neutrons, but if it does, that's an accident.
Okay, so.
Yeah, the electrons are gonna
like,
match the
high protons
protons.
is gonna be 11 for sodium, basically.
Correct,
Okay.
correct. Go for it.
Can you explain like where it says circle any covalent bonds?
Yes, because that's what we're doing next. It's perfect. You had your hand up when we were talking about if anybody was wildly lost.
Sorry, I had a question if that sketch was for Na or sodium, but I think she just confirmed.
Na is sodium. They're the same thing.
Oh,
Yeah.
okay.
Go for it.
Kind of the part where, how come it had 12 neutrons instead of 11?
Yeah, so if you look at sodium 11, the atomic mass as listed is 22.98. So we're just sort of rounding to the closest one, which would take it up to 23. And so if the mass of the protons was 11, the remainder for the neutrons would be 12. Right, to get us up to, what do we have to add to 11 to get us up to 23? All right. So, and of course, there's sodium, I think there's 4 or 5 isotopes. There's like a sodium 20, 21, 22, and a 24, and a 25 or something like that. So most sodium probably has 23 neutrons, but there's a lot kind of around it that is otherwise isotopes of it. So you remember carbon? Yes? How many shells does it have?
2.
2. Which row of the periodic table is it? Second. So how many shells did sodium have?
Oh.
What row of the periodic table is sodium?
3.
The row is the number of shells.
Oh.
Write that shit down. That's a good one, right? That's a good one.
If I don't write everything, I'm very slow, like when it comes like to science and in general, so I have to write everything.
Welcome to college. It's going to be great. It's going to be great. Yeah, so it's like fancy. So potassium is element 19. You see it, the K? How many shells?
4.
Helium, how many shells?
1.
Phosphorus, how many shells? Pete? 3. Yeah, just look at the row. It's the number of shells. You learned that in high school chemistry, though, right?
No.
You learned that in what, Tunisia, Morocco? Team Tunisia, Morocco? Morocco. You learned that in Morocco, right? Cool, awesome. So another question is like, okay, so what are the columns then? What are the columns? The rows are something, the columns are something as well. If we do 1 proton, here's hydrogen, right? How many shells?
1.
This electron that is farthest away, the farthest one out, is referred to as the valence electron. How many valence electrons are there? 1. What column is hydrogen in?
First one.
1. It's like whoever made the periodic table was like coming up with this in a way that like described like what they do and what they are and how they look and how they act. It's amazing.
Can you repeat? I got lost.
I will repeat it by going to my next example. Are you ready?
Okay.
Let's do carbon again, okay? Oh boy, that's a bad drawing. How many valence electrons?
4 and 6. Whatever's the furthest away from the valence.
All right, yeah, so the ones that are, the number of electrons in the outermost shell are called valence electrons. Ignore these things. So like, take the metals out. So you can think about like jump from beryllium to boron. If you take these out, what column is carbon in? 1, 2, 3, 4. So if you take like these metals out, if you take the metals out in the middle, this kind of stuff, and you count over, the column represents the number of valence electrons. How many shells does silicon have?
6.
Shells?
No, 3.
3. How many valence electrons?
6.
Perfect.
Where was this when I took chemistry? I'm serious.
What?
Seriously, where were you when I took chemistry?
Yeah, my chemistry teacher sucked.
Probably on the beach. Fluorine, how many shells?
2.
Valence electrons?
7.
7. Students gonna storm into their chemistry professor's offices after this class and say, I want a refund, ma'am or sir. You did not teach me the structure of the pure. Aluminum, how many shells? Al.
3.
3 shells, how many valence electrons?
3.
You could draw any of these things. You could draw any of these things. How many people are staring at the periodic table right now who took chemistry in the past and said, son of a bitch? Yeah. Yeah. Sorry. What can I say? You not knowing it then allows you to know it now. And it's only day 1. So exciting. Let's draw oxygen. So let's do the oxygen one. But we're not going to do like we already drew. We drew oxygen once. Let's do this. So see the Na kind of on the bottom?
Yeah.
Scratch out the Na and put O2. We're actually going to draw molecular oxygen. Okay? Because oxygen is one of those things that exists in a what do they call it? Diatomic state. You almost never see just a single oxygen atom floating around. It's almost always combined. When you get like gaseous oxygen, it's always combined to another oxygen molecule. So it's always sort of bonded to itself. So if you see it floating around, it's always like this O2 situation. You're breathing in it now. I'm just going to draw the protons because whatever. How many valence electrons?
6.
6. Okay, here's 1. Okay, cool. So how many electrons can fit in the outermost shell, period, like of anything? What's the maximum number of electrons in an outer shell? 8. How many do we have?
6.
Cool. So how many more can we fit in there?
2.
2. So 1, 2, 3, 4, 5, 6, 7, 8. This one can say, ooh, I can hang on to these a little bit. And these can say, you know what, we can do a little timeshare situation here. I can count these 2 in this shell and these 2 in that shell. And now I am sharing valence electrons. So my bond is covalent. Why didn't they tell me that? So this is like covalent bond number 1. It's covalent bond number 2. So each one of them, so why is oxygen, molecular oxygen, so stable? Right? It's acting like all of its valence shells are full. So this one has 6 valence electron, but it's borrowing these 2, so it's an 8. This one has 6 valence electrons, but it's borrowing this 2, so it is up at like a functional count of 8 as well, because it's counting the electron of the other one in its own. And so, as you know, right, when you get to that outermost helium, neon, argon, krypton, xenon, radon, those noble gases that do not react, they don't react because their valence shells are full. So chemistry happens in valence shells. That's where things interact with each other. If we're going to interact with each other, boom, we're going to use our valence skin. It's like my kidney is not going to interact with your liver, right? When we make contact, it's going to be with our outermost layer, correct? Chemistry works the same way. You know, so when you talk about how do we build molecules and all this kind of stuff, the thing that you really want to know is how many valence electrons are there and what shell it is, so I know what I can get up to. So if I draw carbon, my 6 protons, 1, 2, how many things can I covalently bond to carbon?
4.
4, why?
Because it's
Just the outer shell is not full.
So I can put like a hydrogen here, hydrogen here, hydrogen there, small hydrogen here, right? And get CH4,
Ooh.
nothing. Yup. What do you think so far? Perfect. Also, I can do things like, so if I like, okay, covalent bond, covalent bond, covalent bond, covalent bond, that's great. If I wanted to just draw the diagram of it, I would just go like this. And if I wanted to do another one, I could go like, hey, I could bond a carbon to itself. This carbon is always going to have 4. And I could have like carbon dioxide was like, okay, so carbon gets 4 and oxygen gets 2. How do I make carbon dioxide? It'd have to be like something like that. So two bonds for oxygen, 2 bonds for oxygen, 4 bonds for carbon, right? Go for it.
Whenever we get to it, can I try H2O? I think I'm pretty confident about it. Oh, okay.
Perfect.
Oh, you're right, this is nice.
It is nice joke. Only the best for my class.
You don't care if I erase it.
Whatever you would like. Cool. Ladies first.
Are we doing the same now?
Might be able to, sure, couldn't we? Probably could, we probably could.
Even the rest?
You can hang on to it.
Okay.
So we're doing water. Water. Are we there? Are we there?
I can't see the exit, so I don't know if that's the count.
1, 2, 3, 4, 5, 6.
Are our valence shells full? Are our valence shells full?
No.
1, 2, 3, 4, 5, 6. We need 2 more out here. Perfect. We're there? So valence shell is full here, valence is full here. Valence 1, 2, 3, 4, 5, 6, 7, 8. Yep. We're good. Yeah, we're there. We're there. So what's weird about this is that oxygen looked like from the covalent bond state, it looked like it's carrying 10 electrons. It's only carrying 8, but it's borrowing these 2. This looks like it's carrying 2, but it's really only carrying 1, but it's co-borrowing the other one. So it's like, how many electrons are there here total? There's 10. How many protons are totally here?
8.
8, 9, 10. So it's like electrically it works, right? But the distribution, it's like electrically it works, but everyone's valence shell is full. Yes, you can do that by covalent bonding, of which there are 2 kinds, polar and non-polar. We'll get to that later. How did class go today?
Great. Fun.
Perfect. So just a little review. I'm sure nobody learned anything new. Is all this sitting okay? It's good to actually get moving on the first day and actually do something. You feel like you're getting to it. You know, you feel like you're getting to it. Cool. When I can remember to do it and when I can do it well, I do stream lectures to YouTube privately, right? So I can post a link of this to Canvas. So it's like, it's not public out there. It'll be like this class only, right? If anyone wants to go back and it's like, I clearly did not come prepared for class with like lecture notes and a PowerPoint and all that jazz, because I just don't. Because I'd rather do this. Is that okay with you? Because if you can't do it with a piece of chalk on the board, you can't do it. Sad facts, but the sooner we come to terms with that, the better. The good news is you can do it. Demonstrably, you can demonstrably do it. So being able to change the oil in your car, but only in your head, is not helpful. You have to be able to do it on your car. So if you have not yet looked at the Canvas, go ahead and take a peek through, see all the stuff that's there. I think I have a discussion post, right, of like, tell me what your favorite color is using a adjective or something. So blood red is an excellent answer to that.
You got real like into philosophy at the end, like what's the meaning of life?
Well, that's why you're here, right? It's biology class. We talk about life. So what is it? I think I put a homework assignment up there for you to start poking around with. It really is this stuff, this chemistry stuff, I think. But I think it was good to actually get a piece of paper out in front of us and actually start meaningfully doing some actual, the real thing, you know, the real thing. So I hope you enjoyed it. Good? Hope you guys have a beautiful day. You can hang on to those pieces of paper and you can like get whatever you want off of and tweak them or whatever you want. Bring them with you on Thursday. And on Thursday, we'll see you at 9:35. We will not have lab on Thursday. We don't do labs this first week. So after class on Thursday, you're off to your day. But bring those pieces of paper with you because I can give you points for it if you do. The one, yeah, like literally the only one I gave you, right? So yeah, that one, yeah.
What about the other one?